Suppose we have a raft that's 1/4 of a meter thick and 3 meters square. It's got a specific gravity of 0.55, which is about right for some denser types of wood. The question is, when nobody's standing on it, how much of it is underwater? The answer is 55%, because a specific gravity of 0.55 tells us that 55% will be underwater. Now, let's prove that. We'll start with a free body diagram. We have gravity down and a buoyant force up. So clearly we set those equal to each other. And we get rho Vg equals mg. Well, let's be very careful here. The buoyant force is the density of the water times the volume of the displaced water. Let's call that Vs for submerged. And then the mass of the raft is going to be the density of the raft times the total volume of the raft. That's area times height. So let's put an area times height for both, keeping in mind that we're using the submerged height and the total height. Well, the ratio of densities is the specific gravity. That's 0.55. So the submerged depth is 55% of the total depth. And 0.55 times 25 centimeters is 13.75 centimeters underwater. The next question is how many people can stand on it if your average person is 70 kilograms? Again, let's start with the free body diagram. The buoyant force up is countered by the weight of the raft plus the weight of the people. Let's call that the number of people times the weight of a person. This gives us the equation buoyant force equals the weight of the raft plus n times weight of people. Let's plug in. We have the density of the water times the displaced volume times g. In this case, that displaced volume is the total volume because the raft is barely floating. That equals rho Vg again plus n times mg. Here, cancel the g's and solve for n. Plug in our numbers and we get 4.82, which rounds to 4 and definitely not 5, because if you tried to put 5 people on this raft, it would sink. Here we have a water tank that has sprung a leak 1/2 meter below the water line. Keep in mind that these types of municipal water tanks are vented to atmosphere, so the ambient pressure is P0 and not a vacuum. So we start with Bernoulli's equation, and at the depth we call 0 height, we don't have any height, and then at the surface, the tank is so big that the velocity of the draining water is approximately 0. From there we can rewrite it and realize that both P1 and P2 are P0, so cancel those. Solve and you get V equals the square root of 2gy. This is Torricelli's theorem. We plug in and we get 3.13 meters per second, the free fall velocity of something that would have fallen 1/2 meter. Here we have a bottle jack for a car, which combines normal leverage with hydraulics in order to massively amplify force. So how much force would it take to hold up or barely lift this 500-pound mass? And yeah, we're going to stick with English units here because that's what the picture had. Alright, so first thing we need to do is draw a free body diagram because we're dealing with torques. And we have the force F, we have the reaction force of 0.1, F1, and then we have some other force at some unknown angle at the pivot point, which we're going to call O. So let's do our pivot at point O so that we can eliminate that, the same trick we used back when we did rotational motion. The clockwise torque minus the counterclockwise torque has to be 0 Newton meters because we're in equilibrium. Set them equal, plug in RF sine theta, and the sine thetas in this case are both 1 because theta is 90 degrees. At the moment now we're stuck because we don't actually know what F1 is. So let's move over to the hydraulic side of things and take a look at that. Pascal's principle tells us that the pressure in the fluid is going to be the same everywhere, which means the pressure at point 1 is going to equal the pressure at point 2. Pressure is force times area, area is pi r squared, radius is diameter divided by 2. So plugging all that in, we get F1 equals F2 times the ratio of the square of the diameters. Plugging in our numbers, we get 36 pounds. That's a great multiplication. Taking that and plugging it into our original equation, we end up with 1/6 of that, or only 6 pounds, to lift or hold a 500-pound corner of a car. Very nice. In this problem, we want to know the gauge pressure necessary to pump water from a 15-centimeter diameter pipe in the basement up to a little faucet at the top of the Empire State Building with a desired exit velocity. It shouldn't surprise you that we're going to start with Bernoulli's equation and say the point we define as zero height has zero height. We can then take the equation of continuity and solve for V1 in terms of V2. Substitute that into Bernoulli's equation and solve. The math looks a little messy, but it's just algebra. Plug in our numbers, and let's take these individually so you can see the contributions of each thing. The height contribution turns out to be 3,737,610 pascals. The velocity contribution at the top is a mere 12,500 pascals. And, well, the difference in velocities from the bottom is a minus 0.247 pascals. It almost didn't matter. So, adding all those up, you get 3.75 times 10 to the 6 pascals. That's 37 atmospheres, or about 550 psi, and that could create disastrous effects on the lowest floors, so it's not a great way to do things. What they do in buildings like these is they typically have either pressure limiters at various floors, or more likely, they have multiple pumps at different floors throughout the building in order to handle the pressure. Of course, a lot of buildings in New York City have water towers on the top, and they use gravity feed instead, with pressure limiters for the lower floors. If we push on a syringe with a certain force, how fast is water going to squirt out the tip? Well, let's start with Bernoulli's equation. There's no height here, so we can cancel both of those, and the pressure at the tip is going to be atmospheric. It's pushing out into the air. The pressure that we're pushing with is going to be atmospheric plus the pressure that we've added, which is force over area. Substitute those in, substitute in your equation of continuity, and solve. That's all there is to it. When we plug in our numbers, we get 12.7 meters per second. That's about 30 miles an hour. For our last problem, we're going to put a piece of iron on a spring scale, and then lower that into a beaker of oil that is sitting on top of another scale. The question is, what are the two scales going to read in this final setup? Well, let's start with a free body diagram for the iron bar. What do we have? Its weight down is countered by the buoyant force up as well as the force from the spring scale. This gives us the force of the spring scale plus the buoyant force minus weight equals 0 newtons. Plug in and solve. The weight of the iron is mg, the buoyant force is rho vg, and the volume of the iron here is it's going to be its mass divided by its density, which we'll have to look up. That's 7,870 kilograms per meter cubed. If we plug in all our numbers, we get 19.62 newtons minus 2.28 newtons of buoyant force is 17.34 newtons. Now let's draw a free body diagram for the lower scale. Downward, we have the force of the beaker, we have the force of the oil, we have the reaction force of the buoyant force, action-reaction, right? And the scale has to push all of those up. That gives us the force of the scale equals the weight of the oil plus the weight of the bar plus the buoyant force. Plug in our numbers, including that 2.28 newtons from above, and we get 31.71 newtons.